Okay, welcome to this lecture of polymer reaction engineering. In this particular lecture, we will discuss about a brief history of the polymerization processes, monomer and its distribution. Now, why we are emphasizing this about the short history of the polymerization process? Now, if you recall in the previous lectures which we have studied about the small amount of polymerization process protocols and different type of classification streams. Now, in this lecture, because to synchronize the thing that how this particular polymerization process evolved over the period of time and what are the main genesis behind this evolution process, we have introduced this particular segment to this particular course. Now, let us have a look about the short history. Now, history, because when we study about any kind of a history process, sometimes we need to learn about the different type of a shortcoming from the past to improvise our products in the future. And the improvisation process always tutored by various kind of a demand from society, various kind of a demand from the environment, various kind of other demands attributed to the need of time. So, based on this particular approach and this particular concept, various scientists, various engineers, various corporate organizations, they gave a major impetus towards the development of all these polymerization process. Now, see, in past, all these polymeric products, because this polymeric products are very sensitive in nature, because always the eco-friendly polymers, they are the buzzword nowadays. Similarly, if you go for the industrial protocol operation, the energy efficient process, they are the buzzword. Similarly, if you go to the modern era, where the personal protective equipments, different type of gears, different type of drug delivery systems, etc., they are the need of a time. So, based on this approach, scientists, engineers, chemists, they were involved themselves to develop a new process. Similarly, if you see that the start of this particular polymerization process, the Henry Braconnot with the Christian in 1830, they developed the derivative of natural origin cellulosic semi-synthesis material such as celluloid and cellulose acetate. Now, celluloid is a very common or a buzzword in the past era, up to last decade. You may remember that the celluloid films, etc., they were more popular those days. So, they tried to develop this kind of thing, product-based things with the help of a naturally origin cellulose. Recall your classification stream. In 19th century, the nature-made polymers like cellulose, different type of a latex or natural rubbers, starch, they were processed to create a useful goods. That is purely the consumer driven approach. Similarly, Frederick, etc., they discovered the different type of a sulfur to natural rubber to develop automotive tire, etc. In 1840, they initiated the process for the development of this particular thing. Later on, this Charles Goodyear, he developed, because he is, you can say, sometimes are referred as the father of automotive tire. He was born in New Haven, Connecticut in December 1800, and inadvertently he invented the vulcanization process cycle in 1839. Now, it is a boon to the automotive tire industry. In 1830, the Goodyear discovered the sulfur vulcanization of natural rubber by an accident, and in 1844 he received the US patent for his work. Now, see, the purpose of giving this particular thing into this slide is that you see that almost you can say more than 175 years ago, that particular technology was developed, and is still now, from natural rubber to the synthetic rubber to the radial tire to the tubeless tires, etc. So, this is the sequential process of development of these automotive tire industry. So, this process of vulcanization of a rubber, come back to this particular process, this makes it heat resistant without the change in its flexibility. See, when the objective of this particular natural rubber vulcanization is that when automotive tire moves into the surface, then there may be a generation of a frictional heat, there may be generation of certain other things. So, it should not lose its property. So, first thing is that they tried that it offers the heat resistant. Now, this was the first successful and commercialized product in the polymer history, right. So, just try to synchronize the things that how we develop, what was the starting point, etc. Similarly, in 1847, Christian et al., they produced the cellulose nitrate by the reaction of a cellulose with a nitric acid, and which was used as a man-made thermoplastic celluloid in 1860. Now, you can see the application of a celluloid. The film industry earlier it was dependent on this celluloid thing. In 1884, the Cardinot developed the first artificial fiber plant which was based on the viscous rayon and regenerated cellulose. So, that time people were trying to develop the artificial fiber which can supplement the natural fiber, because that was a need of a time, because the population was growing day by day and the demand of the people were on the various spectrum. In 1861, the Thomas Graham they proposed that cellulose and other polymers were collide and aggregated to form small molecules which may be linked together with the unknown intermolecular forces. Though it was starting point, but it gave you another opportunity for the development of all those protocols. Then Hermann Staudinger was a German organic chemist. He demonstrated the presence of the polymer he characterized as a macromolecule. See, different monomers, different molecules. So, they prepare a giant molecule that is referred as a macromolecule. For this, he received a Nobel Prize in Chemistry in 1953. He is also known for his discovery of the Staudinger reaction in the ketene. Now, this Staudinger, they consider the macromolecule as a pure aggregates of small molecules that were closely connected. So, sometimes in the previous lecture, I told you that these polymeric chains are intermingled with each other. They are the macromolecules. On the very next year, the polypropylene followed by the polyethylene, polystyrene, polyvinyl chloride to the list of the commercially available polymers. So, it opens a huge spectrum of product protocols. Then Staudinger proposed that the polymers they are composed of long chain of atom, they held together with the covalent bond, because he felt that there are certain forces, there are certain things must be attributed for this particular joining. So, early in 20th century, he provided the first empirical description of macromolecules, and at the same time new method they were created to assess the certain materials with a unique characteristics. We will discuss those characteristics in subsequent lectures. In 1907, Leo he produced the phenol formaldehyde resin from the polymerization of a phenol and formaldehyde, which termed as a bakelite and used for the thermosetting material, which we discussed in the previous lectures. In 1930, DuPont they produced a new variety of a polymer such as synthetic rubber, nylon and Teflon. All of you are aware about the history of a nylon. It was discovered simultaneously in New York and London. In 1930, the research group developed a model for the distribution of the chain length in the batch reactor from the different polymer chemistries, which was further in 1940 refined to more and more complex and systematic model, which are still used today. Now, just to recall the previous lecture, we discussed that when a monomer gets polymerized, so there are various spectrum of molecules, like if you recall that I gave you this approach that P1, that is the monomer, may get combined with the P2, P1 to give you P2, and this P2 may get combined with either P1 or its P2 itself to give a different product stream like P3 and P4, and simultaneously they may have an opportunity to combine together. So these are, now if you see, if you visualize these things, they are just like these two molecules. They are 3 and they are 4, and if you see that P4 plus P4, they are forming P8. Now by this way the chain gets extended over the period of time. Now if you consider, say, it's a mass, it's a polymeric mass, you will find that P2, P3, P4, P8, etc. So you will find that this polymeric mass consists of various chains having the different chain lengths. So this particular approach being first considered by this particular research group, and they find that this type of a model, and they were first trying to develop a similar type of systematic model for the prediction of the molecular weight of polymeric system. In 1946, a polymer research institute was established by Herman Mark in Brooklyn Polytechnic in the United States, and established the curriculum and pedagogy for the polymer science field. So you may say that what we are discussing right now at this juncture, it was initiated by Herman Mark way back in 1946 to channelize the study of a polymer science, to synchronize the study of the polymer science, and to give a seed of or a food for thought in the undergraduates or graduates in their mind. Now, Poly Division of American Chemical Society, it was formed in 1950 and grew to the second largest division in the association with almost 8,000 members. Now, this is just to give a platform for the dissemination of the knowledge, to the dissemination of other approaches to among the scientists, and moreover it provided a platform for various industrial organizations to come forward for their requirement, so that the scientific community may share its knowledge and jointly together to develop the various products being useful for the mankind. Now, Professor Kenneth George, he is a founder of Brotherton Chemicals, Wakefield. He was born in Luton in 1911, and he was one of the first person or introduced the principle of a chemical reaction engineering in the polymer reaction engineering concept. See, the chemical reaction engineering concept is a very old concept, and if you recall, in the very first lecture I discussed about the formation of ammonia through nitrogen and hydrogen to ammonia. Now, it is not so simple process that if you mix nitrogen and hydrogen you will get the ammonia. There are various things involved in that particular approach. This reaction is exothermic, and again this reaction is a temperature sensitive reaction. You need to maintain a particular temperature over which beyond that particular temperature either the catalytic activity, etc., they may go on depletion, etc. So in case if you are looking for a proper efficiency, in case you are looking for proper eco-friendly process, so you have to maintain certain conditions of pressure and temperature within the system. Moreover, there may be certain side reactions, there may be certain you can say unreacted components, unreacted raw material. which are always the part and parcel of your product stream. So how to separate it out, how to maintain the temperature, how to go for a proper selectivity, how to go for proper efficiency, reaction efficiency, how to make the system eco-friendly. So these are the part and parcel, and what are the different orders of the reaction, what kind of things you need to incorporate in that particular reactor, etc. So these are the part and parcel of your chemical reaction engineering concept. Now, those concepts are equally applicable to the polymer reaction engineering. The reason is that if you recall the previous slide or a handmade slide, where we discussed that the two monomers may combine to form the P2, and then P2 may combine with the P4, P1 or a P2 itself, and again whatever product being formed may combine in a sequential manner with the different type of a product available at that juncture. Now, if you are looking for a particular product, then always as an engineering perspective, you are looking for a fixed molecular weight, you are looking for a fixed structure, etc. So, how to control the things, because this thing, if you maintain the favorable condition, then this polymerization process will go on up to it consumes all the raw material, etc. But sometimes, because it may enhance the molecular weight, so it may become a bulky one, and it may not be a useful product for you. So how to control those things, how to get your desired product. So the similar application of the chemical reaction engineering are equally applied to certain applications, they are equally applied to polymer reaction engineering. So the start the Professor Kenneth, they graded the homocontinuous and heterocontinuous reactions on the basis of a degree of a mixing, right. So just you recall all, just you conceptualize all kind of a different protocols or a different processes or operations applicable for any kind of a process application, and then you try to correlate the things accordingly. Then Carl W. Ziegler, he was a German chemist who together with the Natta, they received the Nobel Prize in Chemistry in 1963 for the polymer research, and they gave the very, you can say, the popular Ziegler-Natta catalyst for the polymeric system. It is a very famous catalyst, and you can say the boon for polymer science. So in 1950, they developed the Ziegler and Natta catalyst based on the transition metal. They allowed to development of a stereospecific polypropylene polymerization process and ethylene polymerization process, and discover the single polymer crystal. So they were the first who introduced this Ziegler-Natta catalyst for the polymerization process. Similarly, the development of polycarbonates from polymerization of phosgene and bisphenol A. Now, the Nobel Committee, incidentally, they acknowledged this excellence research on organometallic compounds, which led to the new reaction, and they opened the new horizon for this polymerization process. The Natta, he was an Italian chemist and a Nobel Prize recipient shared with the Ziegler in 1963. So he began the studying of the polymerization of olefins and developed the kinetics of subsequent parallel reactions in 1938. So he expanded this the Ziegler's work on organometallic catalysis to the stereospecific polymerization. So it was a collective work of both Ziegler and Natta. Now, discovering a new polymer group with the sequentially ordered structure like isotactic polymers or linear or non-branched olefinic polymers and copolymers with different type of atactic structure. So in the laboratory, isotactic polypropylene, they manufactured first on the industrial scale way back in 1957, and this product was successfully marketed as the polymeric fiber or referred as plastic fiber. Now, sometimes the problem of heating of a polymerization was discussed among all the scientists, and this was solved by using an inert solvent as a heat sink, because this is you can say the foremost problem experienced by various scientists in past. So, they used an inert solvent as a heat sink, and by flashing the monomer after condensation outside the reactor. So, the polycarbonate and the polypropylene oxide, they were produced first time by this particular reaction stream. In 1970, the liquid crystalline polymers, they led to the development of aramid, Kevlar, aramid and Kevlar, bulletproof jackets, etc. It's very popular in that sense. So, polyethylene, they form a super strong fiber. Sometimes a liquid crystalline polymer with say 40% of a glass fiber filler, originally developed by DuPont, have wide application in electronic packing, housing, sometimes used in the solar cell applications, etc. In 1990 era, the polyolefin produced with the newly developed metallocene catalyst, which had higher selectivity and a reactivity than the Ziegler-Natta catalyst. So, you see that from 1963 to 1990, they improvised this particular approach. Now, the different hybrid materials, they are sometimes incorporated in properties of both polymer, may be flexible or a lightweight, and sometimes to the solid material, may be strongly packed, etc. So, they may be metal for the conductive properties, ceramic, or sometimes the insulating properties, etc. So, this type of approach is sometimes useful for protective coating with different unique properties. Now, this coating in a broad spectrum is referred as a barrier between the atmosphere and over which you are applying that particular coat. So, they must possess a specific type of properties, maybe inertness towards the atmosphere. Now, we all aware that atmosphere may contain the UV radiation, may contain the humidity, may contain heat or a chilling effect, etc. So, they must provide the barrier. So, these are the food for thought for development of a new material. Now, once we discuss this particular approach related to the history of this one, the purpose, I told you that the purpose of this history was just to give an idea that how this polymeric process being developed and who contributed more in the development of this polymerization process, and what are the school of thoughts for that particular development. Let us have a look about the monomer and its distribution. Now, the distribution part, we have already have a certain idea about that what is monomer. In this particular concept, we will try to discuss about its distribution pattern. So, the word monomer, this can be understood by the splitting into the two different part. One is mono plus mer. Mono means one and mer means a different part. So, they are the smallest unit in the polymeric system, which are joined together with the help of a different bonding pattern, maybe the covalent bond, maybe other things in the different repeating units, which we discussed in the previous lecture. And thus, they form by this joining the complex structure that is referred as a polymer. So, in other words, you can say they are the building blocks of a polymer structure, and they have ability to bond with each other to form a long chain. We discussed this in the lecture 2. So, just a brief that what is the prerequisite for this particular approach. So, they must have at least two reactive groups or some sort of unsaturation over there to form a long chain. Now, the reactive groups, they are sometimes referred as the functionality of those monomers. So, the functionality is the presence of a functional group or reactive groups in the molecules which have an effect on the reactivity of a molecules within the polymer structure. You may say that not every molecule is a participating molecule in the polymeric system. So, they must have an efficacy with respect to the functional group, so that they can become the part and parcel of the polymeric structure. So, on the basis of a number of functional groups in monomer, they can be either monofunctional, they may have a one functional group, may have a difunctional, they may have a two functional groups, and they may have a trifunctional, they may have three functional groups. I will give you some examples of these monofunctional, difunctional and trifunctional, like carbon-carbon double bond. They may contain the vinyl monomer or vinyl monomer styrene, ethylene glycol. They can act as a difunctional groups, etc. Now, let us give you an example of monofunctional. Now, this is you can say here you are having some monofunctionality like CH3OH, this is methanol, and CH3. So, these are the some monofunctional groups. Now, let us have some example of a difunctional. They are ethylene glycol, OH, styrene, sorry, this is styrene. You see here double bond is there. Similarly, H2 and CH2. This is hexamethylene diamine. Similarly, another one is adipic acid. And above all, this is our favorite vinyl monomer. Now, let us have one example of say trifunctional group. Now, this is the glycerol. You see, this is the trifunctional one. So, this may offer a wide spectrum of the functionality, and it gives you a very good source of various kind of polymerization reactions. Now, another part is that the homopolymer. Now, these the homopolymers, they are formed from a single type of a monomer. There may be different type of monomer. So, and it may be the combination of different monomer to give you a different polymeric product. So, they are formed from a single type of monomer, and that is a single type of structural unit, in other words you may say. So, these monomers essentially specifies the properties of a homopolymer. Polystyrene, I gave an example of polystyrene is a hard substance at a room temperature, while polybutyl acrylate is flexible and sticky. So, the best example of these homopolymer are neoprene, PVC. Neoprene is a very common for the sports surfaces, polystyrene, polypropylene, polyethylene, etc. So, these are the examples of homopolymer. In other words, you can say the homopolymer, the repeating units are same. PVC is again one of the example of the homopolymer. There are certain copolymers. Now, copolymer is a polymer formed by the two or more type of monomer. Means if you compare with the homopolymer, here you are using two or more different type of monomer. So, the copolymer, they are mainly having the commercial importance with respect to the polymeric application. The sequential arrangement of the monomer, they are different in the copolymers. So it gives you another opportunity with respect to the engineering perspective, that how you can attach those different type of monomer to one of the base polymeric chain. So the properties of a copolymer depends on types of monomer, their configuration. So a block polymer, usually sometimes referred as the base of this copolymer. Block polymer consists of two homopolymers. They are bound together to form a single polymer chain. So sometimes according to the monomeric sequential distribution, sometimes there are a different type of copolymer configuration, and to discuss all those things you may require the statistical and random. Sometimes they are having the block gradient or a graphed copolymer. So wide variety of copolymer distributions are given in the literature. So let us have a look about the statistical and random copolymer. So in this type of a copolymer, the monomer sequential distribution always obeys the statistical law. Now the random copolymer consists of a randomly bound monomer in a given polymer chain. So sometimes these random copolymer are formed by Markovian zero order mechanism. This is again very popular. We will discuss this Markovian zero order mechanism in subsequent lectures. So sometimes the probability theory applies over here for the prediction of the randomness of all these copolymers, etc. So the random copolymer structure of a polymer usually depend on random attachment of a monomer into the backbone of polymer. So usually what happen, there are a backbone of a polymer, and then different type of other polymer systems or monomeric systems, they can attach together. It is a different thing, and so that you can improvise the property of the polymeric system in due course of time. The best example of this type of copolymer system is polymethyl methacrylate, sometimes with the butyl acrylate, usually formed by the random copolymerization of MMA, that is methyl methacrylate, and butyl acrylate monomer. And the mechanism or protocol referred as the free radical polymerization process. We will discuss this free radical polymerization process in due course of time. Now the pattern of a random copolymer we are going to discuss in this particular slide. Now statistical or random copolymer. Now here XY, XX, X, sometimes Y, XX. Now here X and Y, they are the two different monomer units which are attached into the main chain randomly, like you can see over here. Like this. So this is you can say more discrete type of a thing, and you see that there is no fixed pattern. That is why it is called the random pattern of this particular polymerization stream. There are certain alternate copolymers. Now an alternating copolymer, usually a copolymer, consists of two monomer unit types and distributing in alternating series. The best example of this is polystyrene maleic anhydride, usually formed by alternatively attachment of monomers like styrene and maleic anhydride by the free radical polymerization method. So we will discuss, as I promised, that this free radical polymerization in the subsequent lecture. Now you see that what is the generalized pattern of this free radical polymer, this alternate copolymerization. Again, take back with this X and Y are different monomer units. Now here XY XY, 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 XY and so on. So, you see that this is the alternate copolymerization arrangement. Now, another part is that block copolymers. Now, block copolymers, in this type of a copolymeric system, the blocks of various monomeric compositions are linearly arranged. So, one block is here, another block is here, like this. So, these blocks are the combination of either homopolymer and a copolymer, or copolymer with a different composition. So, the pattern of block copolymers we can discuss like this. Now, here you see that again the same type of monomer. Now, see here, these are the blocks. So, the blocks of a varying monomer X and Y, they are arranged linearly. So, this is the, you can say, the need of a time. Sometimes you may require the different or hybrid property requirement. So, they offer a very good opportunity for this particular product improvisation or process improvisation. There are several examples of block copolymer like polystyrene, block polybutadiene, block polystyrene copolymer. They are having the linear arrangement of monomer blocks of different components such as styrene, butadiene synthesized by ionic polymerization method. Now, this offers a good option or good protocol or process through which you can either improvise the property or you can develop the things. So, in this particular lecture, we have developed or we have discussed different type of chain arrangement. You can go single or homopolymer. We can have a different randomly attached monomers. We are having the different type of blocks of those different monomers. We can have a wide variety. So, before we go into the deep of this reaction engineering concept, we must aware about that what kind of things we are looking for and how we can adhere to those particular things so that we can improvise the thing. So, by this way we are concluding this lecture, and in the due course of time we will discuss about the reaction engineering details. Thank you very much.